All right, so I will give a presentation for the seminar about my PhD project and some of the work that I have been doing. So about me, so I'll be visiting here for 3 months from March until end of May. I'm here with my wife and my small son. I have a background in space and earth physics, a bachelor's degree from DTU, and then after that transitioned into wind energy, where I did my master's, and now I'm also doing my PhD within wind energy at DTU. So I'm working in the Department of Wind Energy Systems, which is located in Roskilde, which is a small town a bit west of Copenhagen. So we're quite big department of more than 370 staff members, and we're distributed onto different sections that have different research topics. So the topic of my PhD project is leading-edge erosion. Some of you might know what it is, some of you might not. It's the phenomena of airborne particles that impact the leading edge of the blade, and then at some point you'll start to have a roughening of the surface, and eventually you'll have the removal of surface material. And this occurs gradually over a long period of time, and it happens over so we have as we just talked about, a 20 years service life for wind turbine typically. It's of course exposed to severe weather conditions during these 20 years of operation. So why do we care about this leading edge erosion? And as I mentioned, the short answer is that it's very costly, and it comes from two main contributions. The first one being that the wind turbine blade is very carefully designed. If you look at the cross section, you will see this airfoil, which is designed to maximize your aerodynamic efficiency. So we typically use the lift over drag as a proxy for this. And when you have a roughening of the leading edge, you'll have an increase in the drag, which reduces the overall efficiency. So this directly causes a loss in your energy production. And I put in here up to 10%, and I think that is can be the case for very severe instances, but more realistically, it might be 1 to 2%. But that is still, considering a huge wind farm over 20 years, 1% loss is still, very significant. So that's the first part. The second part is that at some point you'll get to a severity of this erosion where you would need to go and repair it. There have been cases where you actually have massive holes in your blade. So at some point you will reach a severity where you will violate the structural integrity of the blade, and you need to go and repair it. And just as an example, one of the Danish wind farms close to the Anholt Island had to replace all of their blades after just 5 years of operation. So it's it can be quite costly affair. All right, so my PhD project works on this topic, leading edge erosion, and more specifically how we can use data and data-driven approaches for different applications related to this topic. And I'll list some of the projects that I've been working on during my PhD, and today I'll mainly talk about the 3 that I already finished, and also a bit about 2 that are ongoing. Yes, so the first one is a project called Blade Defects Forecasting. It was a project we did in collaboration with the Danish Meteorological Institute and Wind Power Lab, which is a private consultancy company that specializes in blade asset management. And the main objective of this project was to develop a high-level tool to be used for taking more informed decision on when to repair and how to make preventive maintenance planning in a more informed way. All right, so we basically have 2 types of data. We have the weather data coming from DMI, and then we had some blade inspections, raw blade inspections from Wind Power Lab. And our goal was to sort of find a way of mapping between these 2. So we came up with a processing scheme for the inspection. So you need to come up with a way of making the raw inspections predictable, and you do that by looking at the sequences. So the inspections are performed, and we know the commissioning date of a given wind farm, and then you map that sequence of weather data to sort of that inspection that you perform. And then we came up with an encoding scheme as well, because these inspections come as a form of severity type and severity, defect type and severity. And we need to come up with a numerical ways of mapping these. And then we also had some processing of the weather data that come in. So it's a long period of weather data, and that is being fed into something called an impingement model, which computes the amount of rain that sort of hits the blade, and it's dependent on the wind turbine characteristics as well. Then the modeling itself, we chose to go with an ensemble model, and the concept is that you train a bunch of weak learners. In this case, it was very small neural networks. It works in the same way that Who Wants to Be a Millionaire, where you gather the audience votes, and then you pick the one that has the highest average. It's sort of the same here, where you have a bunch of weak learners that are trained on different splits of your full data set, and then you combine. So each of these models will give you a prediction, and then you can combine the predictions and look at the ensemble means or the ensemble variance to get an idea of your mean estimates and your variance around this estimate. And then we also did some classic validation, statistical validation of the models, and we also implemented some physicality checks where we looked at the actual predictions to make sure that they follow what we would expect in terms of physics. So, for instance, that you can only have damage progression over time, you can't have negative damage. When you have no force, the curve should be at 0, 0. When you don't have any inputs and all these things. So there are a bunch of physical checks you can sort of apply. There's also, with erosion, you have, in the beginning, you have something called incubation period, where you have some sort of period where nothing is apparent on the blade. And then suddenly you have these point erosions, and then your full erosion starts to progress. And then we also want to see this sort of behavior on the curves. And then in terms of the actual tool, or the tool itself, it's an interactive tool that can be used. So we feed it a starting date and an end date, and then it goes in and grabs the data and processes and computes the damage estimates. So here's an example over some stations that we have data from over Northern Europe. On the left-hand side, you see the damage estimates after 1 year of operation. This is the ensemble mean. And on the right-hand side, you see the same plot after 5 years of operations. You see that it is quite local, where you have these the most severe damage, and this is of course used when you do maintenance planning. Okay, so moving on to the second project, it sort of builds on top of the first project that I just presented. It's on the aerodynamic effects of erosion, but not looking at the individual turbines, but looking in the wind farm flow model, so also considering wave effects. So as I mentioned, erosion affects the aerodynamic properties of the blade. And typically we look at individual turbines, and there the only effect comes on the power, so how much power we produce. But usually you don't direct turbines individually, you have them in clusters in the wind farms where they affect each other through the wave effects, like we just heard from past one. And when you have a reduction in your aerodynamic performance or properties, then it affects the power, as I mentioned, but it also affects the wakes, because when you are less efficient in extracting energy from the wind, then you also need more wind in the wake. So it's actually like a counter effect that you have in this. At least that's the hypothesis. And to do this, we have this modeling framework which builds on top of this wind farm simulation tool, PyWake, which is a Python tool for simulating wind farms. It's primarily used for optimization because it's vectorized or runs very fast and can be used for something like layout optimization. And we have built on top of that a leading edge erosion module, which uses this damage prediction model that was presented before. And then it's combined with an aerodynamic loss model. And it's like a simplified blade element model that computes the loads along the blade and then sums it up to provide the power curve and the thrust curve, which are the ones that goes into the wind farm simulation. Then we did a case study for this. We took a reference or a fictive reference wind farm, and we simulated it at 3 different locations in Northern Europe, one in Denmark, one in the UK, and one in Norway. The main difference between these three sites are the amount of rain that it observes during the year. Yes, and we did a simulation over 20 years where we assumed that we did a repair every 5 years. And the columns shows the different sites, and then the top row shows this damage prediction that we do based on the damage model over 20 years. And the bottom row shows the relative power, and it's relative to the non-eroded counterpart. So at the same turbine experiencing the same weather conditions, but not having erosion at all, but still having the wake effects, of course. And what we see is that overall we'll have a power loss, which is, I know it's a bit confusing that it's power loss, and then, but negative is bad, that is the actual power loss, and positive is then like a negative power loss. And what is surprising, or not surprising, but what we hope to see was that we have these periods where we actually have a positive power loss, which indicates that the effects erosion has on the wake losses actually overcomes the effect that we have on the power. And if we look more into the contributions that it has on the annual energy production, we see that the contribution on the power, which is the left figure, shows that it has a negative contribution to the overall energy production. If we look at the contribution to the thrust coefficient, which is responsible for computing the wake losses, we see that it has the positive effect that we expected as well. Overall, it still comes down to a negative effect, so the power overall, or the effect of the power overall overtakes the effect on the wakes. Then I'll jump to the next project, which is a concept of a mitigation strategy for this, which is called erosion safe operation. And the main idea is that you, during the rare periods of heavy rain, you reduce the rotor speed. And the goal here is that you'll have a significant reduction in the damage at the marginal loss in your energy production. But the question is, how often should we sort of activate this operational mode, and how much should we reduce the tip speed? And our approach is to implement this adaptable control strategy, which is based on some reinforcement learning. And as we just talked about, reinforcement learning is like a type of machine learning algorithm that works on a trial and error approach where you have an agent interacting with the environment and receiving feedback. And the goal is then for the agent to maximize the actions to obtain maximize the expected future rewards. That is the neat thing about this reinforcement learning. So we use a specific type of reinforcement learning called Q-learning, which is about learning the value of state action pairs. And once you have done that, you do that iteratively over using temporal learning differences or temporal difference learning. And once you have converged your Q values, then the policy is that you take the action that maximizes the Q value. And the way that you can compute these Q values is, for instance, in a tabular form, but it's not very convenient when you have a lot of states and inputs, and also if you have a lot of actions. So we typically define it as a deep Q network where you have your state space as the inputs and then your Q values as the outputs. And then you can train and update your model parameters using a loss function. So more specifically, we used something called double deep Q network, which is a way of, you have two different networks, one for value evaluation and one for value selection. And this sort of increases the stability of the training. In addition, we also implemented something called prioritized experience replaying, which is a way of more efficiently sampling. So Q-learning is an offline learner where you, at a given time, you sample from a replay buffer. So every time you run your environment, you get some state transitions and you get some actions and you get some rewards. So you will store those in a buffer, and then every now and then you grab a sample from that buffer and you use that to update your model parameters. So usually you use uniform sampling of the replay buffer, but you can make this a bit more efficient by assigning a priority to each of these samples. and then sampling using this priority to make the training more efficient. So the actual problem formulation itself, in this case, we wanted to train like the agent, which is the wind turbine controller, to operate with this erosion safe operation. So the state space that the wind turbine observes is the wind speed at a given time, the rain intensity, and the damage level that we predict using this damage prediction model. So the agent or the wind turbine is able to take actions in the form of reducing rotor speed. So we define this as a single action space with the rotor speed scalar, where one indicates that you just operate normally. We also need to come up with a reward function, and the idea behind this, like we also talked about with the BAS, is that it should balance the income from solar energy and then the cost related to repairing this erosion. And the electricity is sold at a market price. Yeah, so that's sort of the reward that you get, and then the penalty you get is the cost of repair. And the same is the case here as it was for BAS, that you have a very delayed reward because you actually get the cost when you go and repair the turbine. So what we did is that we sort of densified, so we, instead of penalizing the cost at the end, we penalize damage increment instead, which speeds up the training significantly. And again, we did a case study where we looked at a reference turbine, into 10 megawatt turbine. We simulated over a 5 years period, and we assumed some sort of costs. We used this cost function that I showed before. And then we simulated the turbine, given some weather conditions. We have a wind rose showing distribution of wind speeds. And we have the rain rate shown as the cumulative function up on the column to the right. Yeah, and then we simulate this Hornsvej, which is shown located on the west side of Denmark. Then I've also shown here an environment demonstration. So this is just to show how the damage. This is just 3 random episodes generated from the environment without any agent acting. So this is just to show sort of the behavior and see this stochastic process of randomly sampling the episodes. On the left-hand side, you see the damage, which progresses over time, and on the right-hand side, you see the relative reward. So this is relative to a non-eroded counterpart. And then the nice thing about this, looking at just a single turbine and only having these 3 state spaces, that we can evaluate the Q values outputted from the agent directly. So on the left-hand side, we see the Q values for as a function of the rotor speed scalar, and that is for a fixed wind speed and rain rate, and then a varying damage level. And in the middle, you have for a fixed wind speed and fixed damage and varying rain, and the last one is with a varying wind speed. So these are the 3 state space that we sort of feed into the agent. And then, as I mentioned, the policy is by taking the action that maximizes the Q value. So that's indicated by the stars. And this is at the beginning of the training, and then when you train it, you start to see that the agent starts to initially just randomly select actions, and then at some point it learns that it might be beneficial to start taking actions or activating this erosion safe operation. So when you are at the value of 1 in the rotor speed on the x-axis, that corresponds to normal operation. And then at some point the model converges, somewhat converges, and then you will end up with something like this, where you see that this basically indicates your policy. So you see that for certain inputs, it's more feasible to operate normally, but at some point, it's mainly when you have high damage or high rain or high wind speeds, it might be more feasible to activate this erosion safe operation. And then we have also made a statistical comparison with 2 baseline models. So baseline 1 is just using normal operation that is without any erosion safe operation at all. And the baseline 2 is using the most simple erosion safe operation, which is just picking a single rain intensity threshold. So every time it rains above this threshold, we activate erosion safe operation and reduce the tip speed to a fixed value. So it's like a pair. And then we have, for this specific site conditions, we have found the optimal or the settings that sort of maximizes the episode before. That's baseline 2, and then we have the DBQ line, which we train. We see that the baseline 1 is actually quite good. In some cases, when you have very mild conditions, because it operates normally, so in some cases that is beneficial, but it has a very heavy tail on the left-hand side, which is because often it will be way aggressive and have a lot of damage, and that is of course penalized. And baseline 2 is more narrow, so it's more conservative, but it doesn't really benefit for these milder conditions. And then the strain agent sort of grabs the best of both worlds and outperforms. I think it was in more than 99% of the cases that it outperforms the 2 baseline. So it's quite nice to see. Yeah, of course, there are also some limitations in this. This is just a very simple demonstration. It's for single turbine. And one of the main assumptions is that we model this damage at all times. So we assume that it's fully observable, where in reality, we would, of course, be able to model it. But in order for it to be observable, we would have to go and make an inspection, say maybe every 3 months. And then you would collapse your uncertainty on this damage estimate and know the actual damage. Also, we have a very simple model for computing the cost of repair. But also presented this to some of the industry partners, and they completely agree that it's the shape of the cost function follows that it's much more expensive to repair a severe damage compared to doing preventive maintenance at the beginning. Then I also put a sentence here saying AP loss is guaranteed and damage reduction is expected. And what I mean by that is that the industry is very hesitant. They know about this concept, but it's also patented in different ways. But why they're hesitant is that the AP loss is guaranteed, meaning that when you down-regulate your rotor speed, you know that you're going to get a loss in your energy reduction. But the damage reduction is modeled. I mean, you will never know what the damage would look like if you did not implement it. So it's impossible. It's based on these model expectations. Yes, and then I'll talk very briefly about the 2 ongoing projects. So I'm doing a project on a probabilistic erosion risk atlas, and it's based on requests from mainly turbine manufacturers and also turbine owners about having an open source erosion atlas where we can go in and extract important weather features. And the idea is that you would go in and collect long-term mesoscale weather data, and then you would fit some marginal distributions to these wind and rain, and then you would fit a coupler to get the joint distributions, because usually people just model them individually, which is of course, it doesn't make sense, because if you could easily have a lot of rain at low wind speeds and it wouldn't cause any damage. And yeah, so we need to know the joint distribution of this. And then the application would be based on user inputs. So the user would go in and feed in information about which turbine, because you need to know the turbine operational characteristics, and you would also need some information about the material properties. And then the goal is to output probabilistic lifetime estimates, like similar to what we see in the top right corner, where we have the erosion onset time estimate for distribution based on a given site condition. And then you would also be able to get this erosion safe operation feasibility, which means that it's very few rare instances that sort of causes a lot of this damage. But again, it depends on how the joint distribution of wind and rain are for the given site, how feasible it is. Because if it's raining very mildly all the time, then of course it's not very feasible at all. So you need to assess this one. Then another ongoing project that I'm doing is automatic damage detection in rain erosion testing. So we have recently bought a rain erosion tester system like this to the campus in Zurich. And it's a whirling arm rig, meaning that it has like a rotating rig with 3 arms, and then you mount your blade specimens on it. And then it has a bunch of these needles on the top, which can generate a rain field. And then you can do simulate, or you can run a test on your materials in a controlled environment. And then what you do with it is that you go in and then you take a photograph every now and then. So it could be in this case, every 15 minutes, you stop the tester, and you take an image. And then you go in and look at these point erosions. So this is what is called erosion onset time, or erosion onset when you see these erosion points. And then what you do is that you go in and say you find the location on the specimen, and that corresponds to some sort of impact velocity based on the rotational speed and the rain that you generate from this rain field. And then you plug that into an SM curve, like a fatigue curve. And then you fit a curve to that. And then you have some properties that tell you something about how strong this coating is that we have on this specimen. This is all being done manually right now. So you have a specialist that sits and looks through all of these images and on a very big screen and pinpoints all of these points. And of course, it would be nice to be able to do this in an automated way. So that's what we're working on currently. The test has just been inaugurated, I think, a few weeks ago. So it's very early on in this process as well. Yes, and I think that was actually a slide. Thanks.